So just a quick concept. And then we're going to talk about the zeta potential, some additional examples for zeta potential on structural powder compacts from colloidal suspension. When we say the zeta potential is low, the colloid is what? Not very stable. The potential is low, which means it does not have a lot of charge. It doesn't have high potential that overlap with each other to repel each other, which means they have a tendency to agglomerate. And what people observed is, okay, this is for a colloidal silica, okay, colloidal silica, and when the zeta potential is close to 0, and we get such a powder compact from just sedimentation. You let it sit over there. And gradually over time, maybe one day, maybe a week, depending on the particle size, it gradually comes down. But then when you look at the so-called powder compact, when you remove the solvents, dried, this is what it looks like. I have individual what? Sphere particles, okay? Highly spherical, individually dispersed. But between them, I have a lot of what? Between particles, I have so-called between particles. I don't have spheres. I have gaps. I have porosities, right? Okay. So this is kind of an SEM image for a flocculated or sedimented colloidal silica. Okay. For those, because the potential is low, sedimentation happen relatively fast, and the structure is loosely packed with high porosity. On the other hand, when the colloidal is stable due to high zeta potential, I'm going to show you a related image. But this one, the zeta potential is high, 110 millivolt. Okay, and you look at the particles, they are packed what? Much more uniform, much more denser, and the relative pore size appears to be smaller. Okay, so flocculation would happen very slowly. This one you probably have to wait for weeks or even longer. Some of the you probably find if the particle are fine enough, you probably find it never drops to the bottom. Okay, it's densely packed with low porosity and often has feature of ordering. When I say ordering, do you see that within, for example, this one line, another line, the particles are just lined up as a straight line? Make sense? There seems to be ordering, local ordering. You look at local pattern. I start to see local pattern. Unlike here, I don't really see the closed packing. So this is kind of like the zeta potential effect on how fast the colloidal particles would so-called sediment or flocculate, and as a result, the structure, how much porosity, what's the pore size in the compact that you obtained. Okay. Interesting. The more stable the suspension, they would pack more densely. The less stable, they quickly come together, but just like people coming into cure, if they come together, they pack less dense. Okay? So here we give some additional result. Silicon dioxide in water, IEP, roughly equals PZC. IEP iso electric point or point of zero charge is roughly 3 to 4. We're using the polymer PVA as the dispersant. Okay, I'm showing two plots. The left one is showing what? Relative density of your colloidal suspension after it sediments versus fraction of plateau coverage. I'm talking about using this polymer as dispersion, and the polymer would have certain coverage on each of the particles. From 0 means what? 0 coverage means, okay, that's you did not add any polymer into the system, but you have different pH. Okay, the right one is for median pore radius. Okay, for example, you use gas adsorption. Remember the nitrogen gas adsorption analysis? Or you can use SEM. You can get so-called pore radius, roughly the pore size, versus similarly fraction of polymer coverage. So we are having a suspension. What type of suspension? Silicon dioxide in water. And of course, we can control the pH of this thing. But we can also add some PVA, a polymer dispersant or binder into it with different fraction coverage, different polymer coverage on the particles. Okay, so we are plotting it. And then let's just focus on the condition when the PVA concentration is 0. Where is it? It's essentially, it means 0 PVA coverage on these two plots, which is just here on the very left or here on the very left. So we are only focusing here. On the very left, 0 PVA coverage, 0 PVA added. Okay, 0 PVA added. Okay, so we are only concentrating on the very left line. Here we have 2 points. One is for what? pH equals 3.7. The other one is pH equals 7.3. Okay, so we are looking at the case when we don't add any polymers. And we have the suspension. What type of suspension? Silicon dioxide in water, but with different pH. Okay, one is pH equals 3.7, which means what? It is very close to IEP or PDC, which means point of zero charge. Means at pH equals 7, at this open circle, I have 0 charge. I have what? High zeta potential or almost 0 zeta potential? Almost 0 zeta potential. Okay. At pH equals 3.7, I should have very low zeta potential, very little surface charge. I'm talking about this point. Because I have very low surface charge, very low zeta potential, you find, compared with the pH 0.7, it has what? Lower relative density. you got a sedimentation, the powder come together at the bottom, lower packed density. Okay, and at the same time they have what? Open symbol. Higher so-called medium pore radius. Make sense? So okay, I have, when I use a pH for my suspension, when I put that in this slightly acidic condition, my particles are not covered by charge, and as a result, it packs less dense because particles can easily come together, quickly sediment. It packs less dense, and between particles, the pores are bigger. On the other hand, when pH equals 7, which is much higher than the so-called PDC, 0.0 charge, much higher. Now, because I'm more basic, the particle surface are covered by so-called hydroxy group. I'm more basic, higher pH. Each of the particles is covered by a lot of hydroxy group. And as a result, it should have higher zeta potential, more higher absolute value of zeta potential. And compared with solid versus open, I have higher what? Relative density for the powder compact. And at the same time, higher density means smaller interparticle pore size. Okay, that's kind of like what people observed in experiments. when your suspension is more stable, when the particles eventually come together, they pack at the bottom of your suspension. They pack denser because you give it enough time for the particles to arrange and pack denser. Okay? That's experimental observation. And another effect. Here I'm still talking about silicon dioxide. Still, it has the PDC or IEP of roughly 3 to 4. Now we are looking at porosity versus solid loading. What does solid loading mean? How much solid? Here I'm using what? Volume percentage. Within my suspension, how much of the volume is solid? Okay, I'm plotting porosity versus solid loading. And I'm plotting it for 3 different what? pH. I have suspension, I make them certain solid loading, and then I adjust the pH. Okay, and what do we see? The other plot, we're also showing pore radius. And what do we see? Let's say when I'm looking at pH equals 4, pH equals 4. The higher the solid loading in your suspension, in the end, for all 3 lines, it's slightly going downward. Kind of interesting. You make your slurry more and more concentrated. In the end, as it settles, your relative density, your porosity got reduced. Okay. Higher solid loading, the porosity got reduced, but not very dramatic. The effect is not very dramatic. The more dramatic effect is between what? pH. And so what we see, pH is 4, which is very close to what? PCC, which means the suspension, the particles has almost 0 charge, right? Close to PCC, 0 charge, which means they are stable or not stable when I'm here. Not stable. The suspension is not very stable. It tends to agglomerate, tends to come together. And I have high porosity, relatively high porosity. Okay? Because they come together quickly, drop. On the other hand, when my pH is 8, I decrease, getting very far away from what? From the PDC. I have a dramatic increase in the hydroxy group concentration in the solution. Each of the particles now become covered by hydroxy group. They repel each other, and means my suspension is more stable. My suspension is more stable means, okay, if I'm going to have sedimentation, it takes time, but they sediment slowly, but they pack denser, and as a result, I have lower porosity. And this effect is way more effective than what? Increasing my so-called solid loading. You see, let's say from 30 all the way to 55, that's pretty concentrated. I don't decrease it as much, but by adjusting pH, by adding like nitric acid or something, I can make it pack much denser. Make sense? On the other hand, if we overdo it, if we increase the pH further from 8 to 10, which means now my suspension has even higher concentration of what? Hydroxy group. And what do we observe? Actually, the porosity starts to go back again. And what people attribute is similar related to the so-called ionic strength. Now you have just too much electrolyte in your suspension. And too much electrolyte would start to so-called squeeze the balance, squeeze the so-called essentially double layer thickness, and as a result, the repulsion is not as effective. And as a result, I would have slightly higher porosity. And the porosity and the radius is related. Higher porosity, I would also have higher interparticle distance or pore radius. Make sense? So essentially, you say, Dr. Chen, why are you worried about this? It's about, okay, thinking of when you do ceramic processing, what are the knobs you can control to control your microstructure? Because ceramic, we don't often do casting. Because the ceramic's melting point is too high, you cannot cast the metals, ceramics easily as cast metal. That's why you always have to start from powder. And if you start from powder, in the end, you want a dense ceramics. If you start with high porosity, it's very difficult in the end to sinter. You see what I mean? If your ceramic material has high porosity, it's very difficult by applying heat to sinter, to glue the particles together, remove the porosity. So that's why people have to pay attention to what we do in the suspension stage to make the microstructure what you want. Okay? Let's see another example. Now we are looking at aluminum oxide. This one has a PZC or IEP of 8 to 9, slightly basic. Okay? We are also plotting zeta potential versus pH. We saw this before. Somewhere at pH 8 to 9, I have what? 8 to 9, I have roughly 0 zeta potential. And if we are more acidic, I have more positive zeta potential. Okay. On the other side, higher pH than PDC, I have more negative zeta potential. Okay. And then I'm plotting a related plot for powder compaction. For example, you get it from BET, gas absorption analysis. Porosity versus pH. Of course, you see between roughly 7 to around 10, I have higher what? Porosity, because I have lower zeta potential. Lower zeta potential, the particle come together quicker, sediment quickly, doesn't have enough time to pack dense. As a result, it got higher porosity. On the other hand, if we are pH much lower, 4, or on the other side, much higher, I would end up with lower porosity. And if you're going to do sintering, as your green body, so-called before ceramic sintering, roughly where do you want to be, your green body? If you want to sinter it, to remove the porosity, where do you want to be before you sinter? Either on this side, low pH gives me low porosity, or on the other side. If you start from here, means, wow, you may still able to do it, but you have to heat a lot more higher temperature, a lot longer time, which you waste a lot of energy. But here you just can, in principle, you can quickly just by adding a little bit acid, like nitric acid, something like that. Make sense? That kind of gives you the knob to control your process. Makes your sintering more effective, more energy efficient. It's difficult to overcome this porosity difference by sintering. Okay? That's what we said. pH in the middle, we have low zeta potential, high porosity. Okay. On the other hand, we are either low pH or much higher pH, we would have higher zeta potential and lower porosity.